and welcome to Class 3, the basic principles of photogrammetry. So today what we're going to talk about is photogrammetry, and we're going to be using some slides in a lot of cases that I got directly from the PIX4D website. And I'm using these because they match a number of the things that will be in your PIX4D student lab manual that's been provided to us by the company. So I want to remain consistent as much of the imagery here as I possibly can. So what we're going to talk a little bit about today is what is photogrammetry. So we'll start with a little bit of an application of photogrammetry. How would someone in law enforcement, for example, use this technique to enhance their work? Then we're going to talk a little bit about the geometric characteristics of area photos, photographic scale, ground coverage, area measurement, relief displacement, image parallax, ground control points, mapping, and flight panning. And we'll talk a little bit about ground sampling distance. And this week in your lecture, you will get an introduction to PIX4D Mapper. So you have your student account, you're ready to go, but we got a little bit of work to do before we get there. So the first thing we'll talk about is a law enforcement application. So it's been said that an unmanned aviation application, one of the great benefits can actually be to law enforcement, and small unmanned aircraft systems can transform the current practice of law enforcement to enhance it, make it faster, make it more effective. One of the examples where you could use it is and you would use photogrammetry, is in the concept of accident reconstruction work. There are already professionals who do the mathematics, but could we capture the imagery needed for those professionals faster in the field and then get that imagery back to the lab, thus clearing traffic accidents faster? Because a lot of the time that's taken is collecting evidence and collecting data. And can we do that with PIX4D Mapper, or even now PIX4D React? Clearing roads takes time, as I said, and it often causes like a secondary accident. People get frustrated while they're standing in traffic, and then they try, you've been there, you've seen it. I don't need to describe it to you, especially if you've driven through New Jersey. So this can simplify the task, speed up it, but you do need proper training, and you do need to build public support in law enforcement right now, because right now, as we know, drones, as they are not always getting the best public support by themselves. Now, when people think they're starting to be surveilled from the sky, they get a little bit even more nervous about the use of unmanned aircraft systems. So we do need to be cognizant of that as we move forward. So Mecker et al. In this wonderful work, when first looking at what we could do with auto accidents going forward, said the use of consumer-grade unmanned aircraft systems can decrease incident clearance times and provide high-quality ortho-rectified images. And you're going to come to understand what that term ortho-rectified means as we move forward with your lessons here. It's also cost effective. So in 2018, nearly half of all law enforcement drones were the Phantom. The DJI Phantom, which here's a picture of a DJI 4, probably from the PIX4 or from the DJI website. And the Phantom 4 Pro came back. It was so popular. So the price is $15.99 if you buy it from DJI, and a little bit over the DJI cost if you go directly to somewhere like Amazon or a third party. So you're running somewhere between $1,500 and $2,000, maybe a little bit more if you're buying extra batteries that you might need. So not an inexpensive investment, but relatively inexpensive in relation to what you can spend on drones capable of photogrammetry. A lot of people think this is one of the best drones for this at the price point that it's at, because of it's basically inexpensive and its global shutter sensor. And we talked about global versus rolling shutters in the previous video. So, this became a prominent figure. It is lessened some now because of some of the discussion on where did the images go, and concerns about espionage from the foreign manufacturer. So we do have to be cognizant of that, that is happening. So even though it is a very good drone for photogrammetry, we don't know what the future is going to bring. So you always just want to keep that in the back of your head. When it comes to uses like in law enforcement with drones, weather conditions do matter. And they're not built for all weather. They're not going to get you the best evidence collection at night. So we still do have some limitations that we have to kind of think about. But You can buy a cost-effective drone, and if you have a software like PIX4D Mapper, PIX4D Fields, now PIX4D React, you can engage relatively simply in this concept of photogrammetry, which used to be very difficult when you had to do it by hand, but now the computer software has made this a relatively easy kind of knowledge base and experience and skill base to get. So we should define that photogrammetry is the science of extracting measurements from photographs. It has uses in all areas of forensics and many other industries. In the field of forensics, photogrammetry from a drone can be used to solve vehicular crush and to analyze map collision scenes. So what you need to kind of understand is what we're doing is, and again, if we just take the picture, let's say we take the picture on the screen of me, you can't, from a single image, if you were to capture this picture, you can't tell my height, you can't tell how many inches. But if you were to capture multiple images of me from multiple varied points around me, oblique around me, nadir above me, and then link these together by their pixels, you could create a scalable image, and this is what we call an orthomosaic image. But you could put all these pictures together and then be able to actually measure my height, and that's what we're talking about when we talk about measurement. We talk about scaling. It's the idea of creating a scale from a series of pictures, much like would be on a scale of a map that would exist. So it would be scaled so you would actually know distances. So let's say there were two cars, and we'll go over that, and it's in your manual. You'll be kind of processing some of this in your student lab manual later. But if we had two cars and we knew certain things on the ground and the actual distances, we could then take all of the pictures put together in a model and have this imagery for our future use that would tell us the exact measurements on the ground. We'll talk a little bit more about this as we go forward. But it does take a properly trained professional. It doesn't necessarily take the most trained professional, relatively easy training to kind of understand how to collect these images fast from vantage point. And you can do it faster than a person on the ground. So when we say manned personnel with a terrestrial camera, that means a person walking around taking a picture with a camera on the ground. You can do it much quicker and capture much more of the area from a remote sensing standpoint. Bill English always likes to say, look, if you're going to get into this and you're in law enforcement or you're in accident reconstruction, and Bill English is an investigator and a rather famous one from the National Transportation Safety Board, if you're going to get into this, always do 25% of your budget on the drone, 25% of your budget on support and software, and 50% of your budget on training. And again, we kind of talked about this before. Yes, these things become easier, and the PIX4D is designing new versions of the software for industries that make it relatively easy to do. But that training is still necessary, and the understanding of what you're doing and the ability to explain it to somebody else is also necessary. So you can't get away from that. What happened in a lot of times, especially initial, is people went out and thought, oh, I'll just buy the most expensive. Well, the most expensive drones are often more difficult to fly than some of the cheaper ones, and they're certainly more expensive to replace when they haven't been flown correctly. So, think about that, and especially if you're going into law enforcement, you're going to be managing or you're going to be scaling up someone's drone program. The most expensive drone is not always the best option for you, given what you're doing. So, regulations. The FAA still requires either a unit exemption certificate of authorization or a Part 10 that the officers are Part 107 qualified. We obviously recommend that they be Part 107 qualified, because then we know that you've passed the test and you can feel better about your ability to fly the drone. We also recommend it to whether it's future law enforcement officers or law enforcement officers that come to us for training, a UVSI top, so that you not only have the knowledge base of the regulation, but you have the skill set in flight as well. Always put the public interest first. And that's these are recommendations from the literature, not necessarily from me, because there's pushback sometimes from the public with the use of unmanned aircraft. Departmental policies should be developed to ensure the public trust, and this is recommendations police officers make amongst each other. Not coming from me telling someone else how to do their business. Officers using unmanned aircraft with vertical takeoff and landing can maneuver better images by managing their ground surface distance. So in other words, getting closer to the ground, getting a greater level of detail in their pictures. But in order to take these photos, you have to know what they're going to be used for. So there is some, even though they may not be the person processing for photogrammetry, there is some knowledge of what we're doing here that can help you to collect and acquire the images that you need for whoever's going to process it later. So that's why we cover both in this course. We cover it from inception, theoretical, to data and image acquisition, to image processing, to image analysis at the end. And then also, how do we improve accuracy? Basically, what you're doing is you're taking two-dimensional photographs and turn them into a three-dimensional model that's scalable there. Photogrammetry provides a major advantage in terms of data acquisition speed and is easy to use. Accurate and reliable measurement tool that incorporates a reasonable degree of process automation by Fraser et al. But here's the idea. You can get the images that you need. So this is an area where unmanned systems can improve current manned operations, and that's why we talk about it as an application. So we take these pictures. So this is, again, this is an image that you will do, and you will actually perform this on these exact images from your lab manual in a later class. But what we'll do is you take the images from above, and then you start to look at, and in this case you see the green line down here. This is placed on a tape measure that was put out in these images, and I believe these images were originally captured by PIX4D and Drone U working together, and then later incorporated into this manual. So what it is a staged accident scene. Police officers were there, part of a kind of massive training, especially at the beginning of beginning to understand how to use this photogrammetry. And so they laid tape measures on the ground, which allows you to get images, and then you have an exact measurement on the ground that you can then scale your model to, which is one of the things we'll be talking about. But every time you take a picture with the drone, it puts the GPS coordinate on there. And here's what you need to know. GPS sensors vary in their level of accuracy, and a lot of times based on price. So a GPS processor in a Mavic or an AFI or a Phantom off the ground, in and of itself, unless it's like a Phantom RTK, they'll be naturally inaccurate. The sensor is, it's a commercial off-the-shelf drone. It's not going to give you the same level of sensor that our Wingtra drone will with a PPK post-processing kinematics afterwards. But once we have each picture's geographic location, and again, it's pretty good. It's not going to get what they call survey grade accuracy. Then you take the pixels and the center point of each picture, and you begin to kind of tie them together. And here you see, this is done for you in the software, and you'll learn this as you go through your lessons in the coming weeks. But you learn to tie this back to the ground in a certain geographic location, and then pull out those kind of key pixels. The software does it for you automatically, but you start to understand this. So in this, you can see kind of up here in this portion, it's called the ray cloud. So there's a map view because it's geographic. Then there's this pixel representation, and this is where you'll do most of your work, called the ray cloud. And then you can see later there's things like you can do those kind of scalable measurements, height, weight, distance, volumes, that kind of thing. The mosaic editor, you can go in and take out noise or fix images, and they have index calculation and a number of other things, and you'll learn all these in the coming weeks with your lab professor. The nice thing is this was a series of images, again, that PIX4D and I believe Drone U took and created, and it's in your lab manual, so you'll have a chance to process this exact kind of reconstruction accident scene with the materials provided to you. And you can see you start to get the same thing we talked about in the previous video, because all the images are taken from above. That's good. You got issues with the glass, and through the course we'll kind of talk about how you would deal with that. And you have a side, because there were no oblique pictures taken, you can see the kind of distortions. But you do, if you weren't at that accident scene and let's say it went to a jury, there was some kind of lawsuit later, you would have this would give you a better kind of idea of how it was going than just a mere single picture itself, because you're creating this kind of 3D model. And, this is going to be poorly done because it's done by me and my skill set isn't as good as some people with video, but you could probably do a better job yourself. But the software PIX4D will even allow you to create kind of a quick runaround accident scene. So if you wanted to give people the bird's eye view, the aerial view, the side view, however you wanted to do it, you would be able to kind of move through and show what was going on at that accident scene. And people who weren't there could get a really good understanding. Plus, once you've done all the work, you can have exact measurements. You could measure, let's say there had been, because again, this was staged. Let's say there had been skid marks here. You could then go back and do the mathematics required to understand how fast the car was going, the distance, how much brake pressure was applied, all those things, because you would have the information there with you in your ortho mosaic. Another really nice thing about this feature is you can literally take it into Google Earth, what you captured, and bring it to where it is on the planet. So if you needed to explain the geography, it's a relatively simple process to go through. So, as Heen et al. Said, it's clear that the unmanned aircraft vehicle used within traditional police activities appears to garner higher support compared to applications that reflect a proactive yet ambiguous utility. So, if I'm trying to scale this up, and I'm trying to gain public support, clearing accidents, getting people out of the way faster, getting traffic back, reducing secondary accidents, saving lives, that's a good public argument for why drones or unmanned systems can be very beneficial to work, and in this case, police work. But they have applications in archaeology, in farming, in cell tower inspections, in bridge inspections, in historical restoration, historical data collection, you name it, you can probably think of it. So let's go back to the theory of it all. And again, let's start really simply. I'll throw around the words vertical and horizontal, but I will also remember that for some of us, it's been a while since we had geometry in high school, maybe, or even if we saw any in college. So remember, up and down, straight up and down, that's your vertical, they're in red. And then across is your horizontal, there in yellow. So just kind of remember, so when we're talking about horizontal, vertical, you can recall what that means. So remember, we don't live in a two-dimensional world, though, of horizontal and vertical. So we often represent this as the x-axis, the y-axis, and the z-axis to bring it into 3 dimensions. And what we're trying to do, again, is take our images, which we're going to capture x-axis, y-axis, and create that model, which gives you that 3rd dimension, or that z-axis aspect of what we're looking at. Just remember, there's a couple of things. There's with a quadcopter, there's a number of different angles you can get. You can get nadir, the aerial or the bird's eye view from above, looking straight down. We talked about that in the last video. You can get overhead over the image, but at oblique, so maybe at a 45-degree angle. And then, do an orbit around the car, and that will help you adjust some of those kinds of side image distortions. You can take it from a high angle. You could literally fly your drone down to your eye level and, use PIX4D capture, which we'll do, to do orbits and then do overlap that you need. You can do things from first-person point of view. You could shoot from low angle, okay? And this would probably take a terrestrial camera, but you could technically take a picture from the ground looking straight up and think of it as, instead of the bird's eye, now it's the worm's eye view. So there's a lot of options. Some can be done with the unmanned aircraft system. Some probably would not work well, especially like the worm's eye view. But let's talk about photogrammetry, this concept, a little bit. So here's kind of your introduction. Photogrammetry is the science and technology of obtaining spatial measurements and other geometrically reliable derived products from photographs. So what we're trying to do is we're trying to take that 2-dimensional photograph and put it into a geometric and geographic kind of context, what we're doing. So you can determine the scale of a vertical area photograph and estimate the horizontal ground distance from those measurements made from a photo. So how many inches were those 2 cars apart? We could measure to a degree of error. There will always be error, but we'll talk about even in this video, we'll begin talking about how we diminish that error. using these area measurements made on the vertical photograph to determine the equivalent areas on the ground coordinate system. So, we're up vertically, but we're measuring horizontally in a lot of ways. We can quantify the effects of what's known as release displacement on the vertical aerial photographs. So we can figure out the level of error. We can determine object heights, and we can determine terrain elevations by measuring what's known as image parallax. We'll have to go over some of these things. So here's going to be my attempt to explain parallax. Its measurement and 3D extraction conducted from different image pairs can contain offsets. The selection image pair plays an important role in the final analysis. For example, picking a short baseline image pair from a nadir flight may result in low vertical accuracy, and selecting image pairs from the same flight line may make users underestimate the Y parallax and become over-optimistic of relative accuracy. Okay, so this is really, coming right straight from PIX4D and their websites. So what does it really mean? What happens here? So you're flying this flight path and you're taking pictures and you're trying to capture, in this case, that cube at the bottom. But what happens is, because of the angle and where we've moved, there's going to be a level of error over here in the square. So it might be just a little bit off. And in fact, this can be inches off, centimeters off, meters off, yards off, feet off. And the level of distortion will really depend on a number of different factors of image acquisition that we're going to go over. But the great news is PIX4D has the algorithms in it to fix these errors, to adjust to more accurate 3D imaging. And there's other ways and other techniques that we'll talk about to fix these errors, or to at least minimize the error, if you will. One of the big problems is what's known as parallax. And this is in PIX4D's ray cloud. The displayed 3D point cloud is intersected from multiple images instead of one chosen image pair. Users can easily access the calibration result by checking reprojection errors displayed in the properties panel. They can add manual tie points to the region with larger errors by marking and adjusting the position of the images. And those tie points are displayed in real time in the ray cloud. So what does that mean? That means if I do have measurements on the ground that are either exact GPS locations that have been pre-measured, or scalable type measures where I know where I've measured the distance between 2 points, or I've laid out a tape measure that has exact, and if I put enough of those down, I can diminish these errors right in PIX4D by saying, no, this is really your estimation of where this image is really 2 inches off in this direction. It's usually a lot less, actually. So you're 2 centimeters off. So you start to move in a series of the pictures. And then what it does is it takes your data input and addresses this problem, which again, we'll come back to in a little bit, this notion of parallax. We know this is a confusing concept. So we talked about the shutters, global shutter, less distortion, rolling shutter, you're going to get a little bit more distortion, but the software is going to adjust for that and work through that as well. We talked about that. We talked about this the last time as well. Here's for your conceptualization again. And again, these images, when they're green and they're directly from the PIX4D, either your manual or from the website itself, and their presentations and explanations on their website. And I do suggest you go to them. Their videos, their material, very good. A lot of them are in your assigned syllabus. So you have your drone, you have your picture. Global on the left takes the entire picture at once. Rolling on the right takes portions of the picture as the shutter rolls. So you're going to get some distortion there. Your notion of parallax is kind of displayed here. Remember, your drone has, in most part, has one camera lens, but your eyes have 2 kind of stereoscopic viewpoints at something. So we see things slightly differently than the one, and so you get this notion of distortion called parallax that comes from the images from different angles. So, and you know that the images taken from drones is a moving vehicle, so it's always going to be a slightly different angle. Here again from PIX4D, we see this image of a young man who has been knocked off his bike by an automobile, so an accident. And so we see again, how does this work? What angle does it come at? And error, I mean, that's what you need to take from this. You get error from your distance from the images. So this is called ground sampling distance. You get error from parallax. You get error from the angle. You get error from the movement. So what we do a lot in the photogrammetry is we adjust and minimize these errors to get to a more geometrically accurate representation of that area we're trying to define. So the good news is, and again, this used to have to be done when there was no software. Think about the amount of work it would take, because photogrammetry's been around a long time. So people were doing this with pictures, but now with PIX4D and other softwares, it can be done relatively simply, and the computer will fix a lot of these for you, but still there is some manual processing work, and that's basically what this entire course is about, teaching you all these different skill sets with regard to this. So again, science and technology obtaining spatial measurements and other geometrically reliable derived products from photographs. So we need to determine the elements of the exterior orientation of the aerial photographs to create maps and orthomosaics, and we learn to prepare a flight plan as well in this. So geometric characteristics of aerial photos. Aerial photos generally classified as vertical or oblique. All right, so as nadir or oblique, either straight down or on an angle. The nadir in its perfect sense is nearly impossible because of the movement. So you're always kind of getting the images a little bit different. High oblique, if you're too far oblique, you're going to get the horizon. Low oblique does not, and you want to try to avoid the horizon, try to avoid the sky. The sky, think of the colors if we're working off pixels, how hard that can be to identify and to go through. So when we're doing these, we use flight lines. And we're going to use PIX4D capture to decide these flight lines, and you're going to use grid or double grid, corridor. But your model and your choices when you're acquiring the imagery does matter. So that's what we're trying to kind of going over in this video is acquisition. So again, from PIX4D here, and I'll move myself out of the imagery here. Here's what they recommend on their website: 75% front overlap on a single grid mission. So you can see what they're doing is the drone starts at the bottom and it flies this pattern. You're trying to capture what's in this grayed out square rectangle here, and you're going to fly this mission up and down. Each of these red circles represents one photograph being taken. So when it comes to front overlap, so front of the drone, you want 75%. So you want each picture to only have 25% unique. And then that's how it's going to match the picture. It's going to take the pixels in the order it finds them and match them to their identical twins on the other photograph, if you will. At the same time, you need at least 60% side overlap for the ideal. Okay, you need to have the camera pointed straight down. And you need a flight area that extends beyond what you want. So you can see here on the outer part of this rectangle, all these red dots are actually not over. That way you get the side overlap here from this, or the front overlap up top, depending on where the drone is located. So that's an important element as well. Now, there's another option when you're picking in PIX4D capture, and that's called the double grid. And you can choose, and this is going to give you, as I'm going to show you in a second, this will give you more accurate, but it's more to process as well. And that's kind of the trade-off on these decision-making process from your standpoint. That's where your skill set comes in. If you do a double grid, then your overlap is 80, the PIX4D recommends 85% front, 70% side, and slight oblique camera angle obtains greater coverage of the area. So you can start to see there's going to be some pictures that are going to be almost identical on where they are because you've flown two grids, but you get a lot more representation of the area in a double grid pattern. Why would you not always fly a double grid pattern? Well, it could be very windy. It could be time. There could be elements of practical interference by objects around. There's reasons why you may never fly a double grid, but if you can choose between the two, you want to do that. Now let's go back to our police example. Here's where a corridor, and this is another option you can choose in PIX4D. This is a slide from them. If you're doing this kind of corridor mapping plan mission, 85% front, 60% side, and at least one flight line beyond the extent. So, picture this as a road. It's a nice way to see it. So you're out above and outside the road, flying this. You make sure you're outside the area that you need, and that's going to give you, in the end, the images that you need to kind of reproduce what you're doing, or what you might want in your ortho mosaic. So here's a nice photograph from PIX4D. Again, shows you kind of the differences. It's obviously a bus parking lot, and you can see the single grid. You see on the left-hand side, you'll see a lot more distortion than the double grid. So you're going to start to see more images mean more accuracy if taken correctly. So double grid is going to give you basically somewhere around twice the number of pictures, and you're going to get some more accuracy, but you're not going to get rid of all that distortion. You can still see some distortion here, but comparatively speaking, you've moved a great deal. Again, from PIX4D, and remember this because where we fly, we often have mountains, so we have terrain issues we have to look at. There are a couple ways to deal with terrain, and again, everything about this is moving towards how do we get more accurate, how do you get more accurate. Simple is fly a single flight at the same altitude. Practical compromise, multiple flights at different altitudes but the same distance from the ground. And the ideal is a terrain following image acquisition, and not every drone is capable of that. So that's why you have to do this in different ways depending on your geography and depending on your skill set. And it will take some time to learn, especially in a terrain like ours where you have elevation changes. This is science, of course, but your ability to capture the images correctly is somewhat artistic. But I wanted you to be aware that there's terrain issues. Just to kind of remind you about the overlap, you have an area of interest in green. The front overlap is necessary, and those numbers that PIX4D recommends will become really ingrained in you as you move through this course. And you have to have the side overlap, and in order to do that, you need to know the image width and the image height, which the good news is has already all been programmed into PIX4D, which is why we use it. So any of the drones you're going to be using in our program are drones with cameras that have already been programmed into PIX4D, so it makes it nice and easy. If you want NLAP, it requires a 50% overlap to generate what's known as stereoscopic coverage, so diminishing that parallax, if you will, where adjacent pairs of vertical photographs create stereo pairs to provide two differing perspectives of the ground area. People would manually create maps and models from overlapping photos, but the good news is that was the old days. Now with PIX4D, we can all be an artist. We can all create a model, right? So just remember, there is photographic scale. So just like maps, vertical aerial photographs can be defined by their scale. The scale determines how large of an area is covered by a photograph and in what detail. Understanding scale is key to selecting and obtaining appropriate aerial photography for a project. All right. And this is when we get into, okay, this is where we're going to talk about GSDs, or ground sampling distance, a great deal in this class. And think of it like this. Basically, ground sampling distance is how big each pixel is on the ground. Okay, so if you're closer to the ground, your pixels are going to shrink. And that's going to give you, and as you pull those pixels back together, that's going to give you a greater degree of accuracy, a greater degree of visual representation. If you're higher in the sky with the same camera, then your pixels are going to get larger. And again, as you try to put things together, you have less detail that you've collected then. So there is a trade-off when you're doing this. So a ground sampling distance of 5 centimeters means that 1 pixel in the image represents linearly 5 centimeters on the ground. So 25 square centimeters then. And a GSD of 10 meters means that 1 pixel in the image represents literally 10 meters on the ground. So that's really what you're getting. You're trying to say, okay, what area, what geometrically, how much area is there when I'm at this altitude, known as ground sampling distance. So if we look here to kind of give you an idea, we're looking at ground sampling distance. Again, another one from PIX4D from their website. On the left-hand side, it's a 2.5 centimeter ground sampling distance. Look at the level of detail you have there. Now, if we went way high and we got 25 centimeters ground sampling distance, well, you see the pixels have grown so large. I mean, I guess you could say you can probably, well, I don't, if you handed me this, would I know it was 2 cars? I'm not sure. Seeing the 2 cars there, it becomes very clear to me now. But you can see, get closer to the ground, get more detail, get more accuracy. Realize, though, that even when flying at a constant height, the images of a project may not have the same ground sampling distance because of that elevation we talked about before, and also changes in the angle of the camera while shooting pictures. Since the orthomosaic is created using the 3D point cloud and the camera positions, an average ground sampling distance then is computed and used. So, you know, it's going to identify, because of the patterns of the pixels, it's going to be able to tie everything together, but then it's going to have average out that ground sampling distance. So again, directly from PIX4D website, they would say the ground sampling distance is the distance between 2 consecutive pixel centers measured on the ground. All right, so you got 2 pixels, and what's the distance between the 2 centers of those pixels? The bigger the value of the image ground sampling distance, the lower the spatial revolution of the image and the less visible the details. The GSD is related to the flight height. The higher the altitude of the flight, the bigger the ground sampling distance value. So when you read this and you kind of think about it, you're like, okay, well, just fly really, really low. And if that's possible, do it. So sometimes that's not possible. Sometimes it's not practical either, because there is an aspect of, well, how close do you need to be? And can we fix some of these distance issues and inaccuracy issues other ways so we collect less pictures? So again, if I'm going out there to an accident scene and all of a sudden I'm like, well, I want this really, really accurate, I'm going to collect 1,000 images. Yeah, you're going to have a very accurate, but how long will that take? And again, remember, some of this is about efficiencies. So if I can get the same level of accuracy with less pictures, then I have less processing, so maybe higher. Sometimes you can capture more area with higher. So if my geographic area is huge, and I'm flying a quadcopter that can do a certain amount on a battery, you know, you can be out there for days doing this. Some of this. So again, so if you go higher, you might get done faster and you might cover a larger geography. So it really does come down to what you're trying to do. So what will you hear in this class? You'll hear about 2 centimeters a lot. 2 centimeters. Let's try to get as close to 2 centimeters. Well, why? Well, that's what's considered survey grade accuracy. So if you're down to 2 centimeters, you have enough accuracy for what land surveyors would be able to do. So they could literally certify your map or model based or of geography if you got down to 2 centimeters and they trusted the process that you did it at. Remember, taking this photogrammetry class does not make you a land surveyor. You are not a land surveyor. I am not a land surveyor. Your job is to practically apply this and be a person who can collect the data in an accurate fashion over time. So there is some variation here. You know, you can't always capture every image you want. You can't always capture. So understanding and knowing this. So again, from the PIX4D website, you have the ground sampling distance calculations here. I don't need you to understand all the calculations because the software is going to do it for you. And in this degree, we don't cover that in that much detail. That part of it, you will cover a little bit in your technical math course. But here's what I do want you to remember. Altitude matters in ground sampling distance. The ground sampling distance, which is the centimeters distance between pixel centers. The focal length of your camera matters. How many millimeters? So, better the camera, but it's also more expensive. So again, you got that trade-off, especially if you're starting a business or you're trying to do this professionally. Do you really need, you can't go out and buy a $50,000 drone all the time, right? For every job you might do. And then the PS stands for the pixel size themselves, because remember, as ground sampling distance increases, the pixel size also increases. So you can calculate this. It's going to give it to you on PIX4D capture. It's a part of what you look at. You're measuring your ground sampling distance there. But let's say you didn't have that. Let's say you were using another software, or let's say you wanted to pre-plan out your mission. You have ground sampling distance calculators in your syllabus. Propeller Aero has a really nice one. PIX4D has one. And 3D FlowNet. And what's nice about these calculators is they have the drone that you're going to use plugged in. So each of them has basically a different set of drones that they've kind of measured out. The more common drones are probably in every one of them, but these are a couple good calculators. Check them out. Look at ground sampling distance, just so you understand it. A lot of the time, though, we'll determine that when we're using PIX4D capture. And we do have basically a standard definition and suggestions that your professor will go over with you in class. But here, just kind of remember, so assuming everything's the pixel size, you can start to see here in this kind of sensor revolution, 42 megapixels is going to let you fly higher and capture more. 16, 12 megapixels. But remember, if you're trying to do this from video footage that you've captured, the best any 4K video is going to get you 8.8 megapixels. So there's another problem. It's science, so there's a problem. There's a solution too, though. The relief displacement is the radial distance between where an object appears in an image and where it actually should be according to the planimetric coordinate system. The images of ground positions are shifted or displaced due to the terrain relief in the central projection of an aerial photograph. If a photograph is truly vertical, the displacement of images is a direction radial from the photograph center. So the displacement emerges as we move out from the center of the picture. It's called radial displacement due to relief. The radial displacement due to relief is also responsible for scale differences within any one photograph. And for this reason, a photograph is not an accurate map. So you can't, but when we put all the photographs together like PIX4D does, then it does address this issue. And that error is corrected for you. There are other ways where we get more accuracy, and we'll talk about these throughout the course. So when you're flying in the Smith Training Center, we have professionally placed ground control points there that give you the exact longitude and latitude in the center of them of where that sits. So you have that as a correction, and that's one of your lab manual exercises. You're going to work with GCPs. We have the DJI Phantom RTK drone, and what this does is it uses a base station. It uses a better GPS sensor in the drone itself, and we'll go over this in a lot more detail. I'm going to go over this very 30,000 foot overview here. It works with the GPS satellite to give you a more accurate and more accurate kind of geographic geotags that it's going to put on each photograph because of the various ways you've used the real-time kinematics. And what you need to kind of keep in mind is the expense here. GCPs, let's take our police, because we used that as the beginning one. You can't get a survey person out there to set exact GCPs on the ground anywhere a random accident happens. RTK could be a solution, but you're talking about a very expensive, $10,000 kind of drone there. PPK is post-processing kinematics. That's where you would take data from GPS data from local coordinating stations that are around you to kind of fix after the fact the inaccuracy in the geotags within the drone itself. So like an example of our drone, the Wingcher 1, uses PPK. Scaling, or what I call the poor man's version, is where we're going to put those scaled measurements on the ground, and that's going to be your final project exercise. And what you're going to do then is measure those and go into PIX4D and fix photographs individually and move them. So the geotags from GPS are automatically there. So all this takes, behind the scenes, takes an incredible amount of mathematics and mathematical algorithms that you would have had to do without PIX4D, but PIX4D is going to do this all for you. And you can use all these methods to correct error in there, to geographically place the pictures exactly where they belong, and also make sure that if there is something on there that, let's say, we'll use the car again. Let's say that's an 8-foot car, that in your model, the car is actually representative of 8 feet, for example, or 10 feet or whatever the car might be. And we do that by having those predetermined, tape. You throw a tape measure on the ground, you measure distinct points around the accident. And these are called, these are also called ground control points, but we haven't linked them professionally. We just threw them down and we measured point to point, center point to center point on them. And then we use that, and you'll get some accuracy. When we talk about ground control points, let's talk about relative accuracy and absolute accuracy. So relative accuracy is the accuracy that is defined by comparing individual features on a map. A reconstructed model, an orthomosaic with other features on the same model. For example, 2 points of the model can be 2 meters away from their real position on Earth, but if their relative accuracy is high, then the distance measured between these points will be very accurate, as it is related with the relative position of the points. What does that mean? That means you can get to, and think of the ground sampling distance, think of whatever measurements you use. The relative accuracy can be adjusted and amended. Absolute accuracy, slightly different, is the accuracy that is defined by the difference between the location features on a map, reconstructed model, orthomosaic, and their true position on the planet. So, when you're there, it's absolute, right? But when we get into the software, the images, and we're recreating, we're at a relative accuracy, and we're trying to get that relative accuracy to the ideal, as close to the ideal 2 centimeters as possible. It'll never be absolutely accurate. There'll always be some degree of error we cannot overcome, but we know what a threshold is. So the ideal threshold we'll talk about is 2 centimeters. When we're reducing error, and again from PIX4D, image geotags are going to give you a variable level of accuracy. You need to have a reference measurement, so it's acceptable. It will vary on where you are. It will vary on how many GPS satellites you have. It will vary on terrain elevation. It'll vary on your ground sampling distance. But you'll be able to reconstruct something. Okay, its level of accuracy you'll also know, but but it may not be accurate enough for whatever you're working on unless you use some of the more advanced things we talked about. So if you just fly the drone, you're going to probably, and the images are geotagged, you're probably for most things going to get something to a level of scale of acceptable. We can use scaling, what's known as a scale constraint here, and that's a good. So that's a metal tape visible in the project. So you can literally say, oh, PIX4D thought that this 20-foot tape measure was 19 inches and 9/10. So, but it really should be 20 feet. And you can fix it in a number of pictures, which would then fix it in the entire model. So another thing that people might use is something called a total station, provides survey grade, but not in position to the real world. That's going to give you a better imagery. It's expensive. It's hard to use. Think here, RTK, PPK. The best is going to be exact GPS location. So exact ground control points that provide the real world location to survey grade accuracy. And again, your access to this in the field, it won't probably be there for the most part, unless you go to work for a huge surveying type company and you're going through all this. Most of the time, you're going to be in the acceptable to good area, and it's pretty good. When you just have the geotag that the drone GPS sensor provides and places on the picture itself of longitude and latitude, realize that you're relying on the flight computer to automatically geotag. Depending on where you are and the conditions where you're flying and the terrain, you're probably going to be anywhere from 3 to 5 meters of accuracy horizontal and probably 10 plus meters in elevation. So it's going to give you an estimate. It's going to estimate its elevation on how long it takes the signal to go from the satellite back, but there's going to be an accuracy here. And when you think about it, when we're talking about 2 centimeters versus 3 meters, which I can't even reach to, there's a huge amount of inaccuracy that can come with just geotagged photographs. It's not a substitute for ground control points. And remember, even if your drone has RTK or PPK, it doesn't always use it to geotag the images because you have to set it up and make sure it's working properly and know what you're doing. So, and again, you'll see there's your scale constraint there, the tape measure. This will come later. You'll be actually processing these exact images from the PIX4D manual you're working on, but you can reconstruct in relative space. All right, so position, no. Orientation and scale, you're going to be able to get to. Exact position, absolute accuracy, unknown. Relative accuracy with scale constraints is going to vary based on how many scales you have that you're measuring back to, based on your ground sampling distance and a number of other factors. But if you had GCPs, let's say you had points on the ground that had an exact location and you knew the exact longitude and latitude, then you're going to get position, orientation, and scale. And your horizontal and your vertical ground sampling distance, you're going to get closer to absolute accuracy, and you're going to get close with your relative accuracy as well. They're going to be almost the same in reality. So we talked about ground control points. So what are the ideal? It depends on who you talk to. We like our red and black that we have. Drone U likes its yellow and light blue. But the most common ones you're probably going to see out there and for sale are some kind of static, flat matte finish that highly contrasts, like black versus white. And they should be at least 10 times the average ground sampling distance. So the size of your ground control point needs to be at least 10 times your GSD. And you need to have a discernible center at the pixel. So right here in the middle, that's what you're going to measure. So you could throw 4, let's just say you had, these in a kind of cloth-like fashion or a hard plastic. You could throw them out at an accident scene. And in addition to throwing your tape measure on the ground, you could literally measure from the center point of one to another and record that relatively quickly, then fly your drone mission. And so when you got back, you could take all these scaled measurements and accurately kind of put more accuracy into your model. If you knew the exact, like the ones we have placed at the college that you'll walk out around the Smith Training Center and see, then you can go back and just plug in the actual numbers of GCPs, and I think that's going to be in lesson 3 of your student manual. You'll learn how to plug in if you had ground control points, and this will become all more clear as you go through the lessons in the manual as well. So when we're using GCPs, there's a lot of argument here. PIX4D, this is from PIX4D. They're going to say a minimum of 5 to 8 per project, evenly distributed throughout what you're trying to capture. So you can see there they put 5 down and they put it nice and even. So if you are going to use these, then you want to use 5 to 8. Is kind of a idea. So here's one they took, and it 2,892 images with just the geolocation, 630 acres, so a large area, ground sampling distance of 4 centimeters, and then GCPs. So what was their error then with no GCPs? It was 4.4 meters. If they had 5 GCPs down, then it went down to 9.8 centimeters, 12, 8.1, 20, 8.0. And so you can see that just putting those 5 ground control points in, measuring the distance between, or having an exact GCP location, you can start to diminish that level of error that you're experiencing in your models or your maps. Now, 12 is an important, so the literature, if you go in and read literature, and people have been doing this, all right, so what is ideal? So, okay, there's theory on this, there's some argument on this. As this comes about, there's constant kind of research being done by universities and other professionals to figure this out. Here's what I can kind of tell you. PIX4D is going to tell you 5. I'm going to tell you 7 is the starting point you want to be at. But I'm also going to tell you that 12 is where you get what I would call, if it was an economics class, the law of diminishing returns. And you can kind of see it there. From 5 to 12, you're getting that roughly 1.7 centimeter difference. But when you add 6 more, you only drop a tenth of a point on a centimeter scale. So what's happening is after 12, it's just not worth the effort. So 12 should be your maximum at any given, because you're not going to get any more correction on 13 through 20 there. And I would argue 7 is your minimum. But PIX4D is going to tell you 5. And we're doing some research now at the college where we're trying to see if, with more accurate drones like the Wingtra or the RTK or the EB, can we get below 5 and get the same level of accuracy? So, again, there's a lot of literature, there's a lot of research being done in this area to kind of determine what the ideal is. So when we're doing georeferencing, or putting those longitude and latitude on our picture, with the acquisition. So you can use something like a total station according to PIX4D and collect coordinates with survey grade instruments. If you don't have those, a cell phone, a handheld GPS, Google Earth can help you georeference. You can document GCPs for reference when you're processing. So you might draw out a rough sketch of the distribution and the contextual photos, figure out where they're going to be. You might measure between them, scale, if you don't have that, but you do want to document where they were when telling a client or anything. And if you have surplus measurements, withhold when processing and use them later after the fact. So once you've initially processed, then you're going to go back in, fix the things, add the GCPs, reprocess. So if you had more than 12, let's say, you could then use those extra ones to go back and say, okay, now that I've reprocessed, where's my level of accuracy on the ones I haven't fixed? Because they should be adjusted as well as the measurements you've actually fixed. So it's a good checkpoint kind of thing. What will we go over in your course? Not in this class per se, but in this session, but in the total class throughout the semester, you're going to learn a lot about geotags, and you're going to do practical applications. So this will become much less theoretical, much less on the video, and much more clear. You're going to work with actual survey grade GCPs that we've had put in place so you can see the difference. You're going to work with RTK. You're going to work with PPK. Hopefully you're going to work with arrow point ground control targets. These are ones we throw out and it actually gets the exact location. And you're going to use the cheapest drones that we have to do it scaling so you can have the poor man's version. And then what you're going to do ultimately at the end of the semester is measure which is the most accurate and what's the degree of accuracy differentiation between all these methods. So that hopefully by the end you say, oh, I don't really need to spend $10,000 on a drone. If I have techniques that can get me to $10,000 worth of accuracy, I can save myself a lot of money. So you'll chart and measure, and we'll talk ultimately about the statistical significance. Remember, part of the course is also about flight planning in addition to these technical aspects we've talked about. So you're going to use existing data when possible. So you're going to go through your lab manuals in the coming weeks. Starting this week, PIX4D has provided us and you with great imagery that you can use, a manual you can follow. You're going to go through that. We'll talk also about cost versus accuracy. How much accuracy? You don't always need to be 2 centimeters. Okay, that's what a survey grade needs for an engineer to certify. But most of the work you'll ever need, you'll never need that level of accuracy. But making it more accurate is not necessarily a bad thing, and having that skill set. Um, Drones have really, and realize this, reset the parameters on these decisions. And as the pilot, this is where the skill set is. What ground sampling distance do I need to get my client? What end result do they need? What level of post-processing work do I need to do to get them the level of accuracy that this project requires? All that takes skill, takes knowledge, and that's what we're doing. That's what this course is about. So we're going to use flight planning software, and by this I don't mean Skyward. Skyward's to plan out your flights, but we will use PIX4D capture throughout this course to collect our data autonomously. However we're going to do it. We'll do a little bit of a kind of, at one point, a manual kind of comparison just to show you that autonomy really is beneficial when doing this kind of work. And you're going to learn how to do these flights, and you're going to learn how to plan them in the field. You're going to learn how to collect this data. You're going to learn all of this stuff throughout the course, and you're going to learn how to correct things. And some of the concepts we went over today that may still be very kind of abstract to you will become much more clear as we move through the course. I'm Dr. Will Austin for Warren County Community College. We'll see you in the next video.